I have no idea what happened. I think I need to go over this like 20 more times to fully understand. Hi friends, welcome back to the channel. My friend forced me to go to the gym this morning and now everything hurts. If you're new here, my name's Ash, I'm 27, I'm a cybersecurity enthusiast, and on this channel, we play Capture the Flags and learn all things cybersecurity and hacking related. On today's video, we're going over day 8 of the Advent of Cyber 2022 event happening from tryhackme, and if you need anything like a playlist to the other videos, timestamps, or helpful links, you can find that all in the description. Okay, let's jump into it. So over on tryhackme, we've got day 8 or task 13, smart contracts. So we have another great walkthrough to go and watch, and we've discovered that the company was now on the blockchain attempting to mint their crypto, and they were quickly compromised. They've lost all the cryptocurrency in the exchange because of the attack, and it's up to you as a red team operator to discover how the attack exploited the contract and attempt to recreate the attack against the same target contract. So we're going to be diving into smart contracts and the blockchain, why that's all important. We're going to understand how contracts are related and what they are built upon and some core functions, and then understand and exploit a common smart contract vulnerability. First area is, what is a blockchain? So what's mainly been used for financial technology, such as cryptocurrencies, it's now expanded into other industries and applications. So we can think about a blockchain as a database to store information in a specific format, and then it's shared among members of a network with no one entity in control. So a digital database or ledger distributed among nodes of a peer-to-peer network. And this is where we get the term decentralized. Unlike a single server housing the database, it is shared among all the computers or nodes on the network. This means everyone is essentially maintaining the integrity of the blockchain, and if one member is trying to modify something in a malicious way, everyone or other members would have to compare it and cross-reference. See if everybody should have that change. The whole goal of a blockchain is to keep data integrity, and it's implemented using cryptography, and this negotiates transactions and provides utility to the blockchain. So we're sort of going to ignore the blockchain itself and instead focus on cryptography and how data is transferred and negotiated. That brings us to the next section, introduction of smart contracts. So smart contracts are most commonly used as the backbone of DeFi applications or decentralized financed applications. And this supports cryptocurrencies on a blockchain. So a DeFi app facilitates currency exchange between two entities. Person A wants to pay person B. The smart contract, sort of like the middleman and defining the details of that exchange of money. So a smart contract is a program stored on a blockchain that runs when predetermined conditions are met. So smart contracts are just really any other program created from a scripting language. So languages such as Solidity, Viper, YUL have been developed to facilitate the creation of contracts. But you can also use traditional programming languages like Rust and JavaScript. But at the core, smart contracts wait for conditions and execute actions similar to traditional logic. It's like everything else, it's just a program. Next section, functionality of a smart contract. Building a smart contract may seem intimidating, but it greatly contrasts with core object-oriented programming concepts, something that I really struggled to learn and have no grasp on still. So before diving too deep, let's imagine contracts. A contract was a class. So depending on the fields or information stored in a class, you may want individual fields to be private, preventing access or modification unless conditions are met. So a smart contract is pretty similar. Information may be private or only accessed or modified from functions defined in the contract, and a contract commonly has several functions that act similarly to accessors or mutators, such as checking balance, depositing, withdrawing currency. Once a contract is deployed on a blockchain, another contract can then use its function to call or execute the functions we just defined above. So if we controlled contract A and contract B wanted to first deposit one Ethereum and then withdraw one Ethereum from contract A, contract B calls the deposit function of contract A. Contract A authorizes the deposit after checking if any predetermined conditions need to be met. Contract B calls the withdrawal function of contract A. Contract A authorizes the deposit of the predetermined conditions for withdrawal are met. Contract B can execute other functions after the ether is sent from the contract A, but before the function resolves. Clear as mud. I don't know why, but this is actually like confusing the heck out of me. I think it'll start to make a bit more sense to my brain if I start downloading the files and start playing around with things. But I mean, essentially it makes sense, right? You know, specify some rules before the transaction can actually be approved and can happen, so make sure those rules are met. Like, I feel like I'm getting the basics, but it's still a little confusing. Okay, next section, how do vulnerabilities in smart contracts occur? So these vulnerabilities arise due to logic issues or poor expectation handling. So when conditions are insecurely implemented through the previously mentioned issues. So taking a step back to contract A, these conditions of the withdrawal function are balance is greater than 0, send Ethereum. So at a first glance, this may seem fine, but when the amount is sent to subtract from the balance, referring back to the contract diagram, is only ever deducted from the balance after Ethereum is sent. Is this an issue? The function should finish before the contract can process any other function. But if you recall, a contract can consecutively make new calls to a function while an old function is still executing. An attacker can continuously attempt to call the withdraw function before it can clear the balance. This means that the predefined conditions will always be met. A developer must modify the function's logic to remove the balance before another call can be made, require stricter requirements to be met. Next section, the re-entrancy attack. So we informally introduced a common vulnerability known as re-entrancy. Reiterating what was covered above, re-entrancy occurs when a malicious contract uses a fallback function to continue depleting a contract's total balance due to a flawed logic after an initial withdrawal function occurs. We have broken up the attack into diagrams similar to those previously seen to explain this better. Assuming that contract B is the attacking contract and contract A is the storage contract, contract B will execute a function to deposit, then withdraw at least one ether. This process is required to initiate the withdrawal function's response. Note the difference between the account balance and total balance in the above diagram. The storage contract separates balance per account and keeps each account's total balance combined. We're specifically targeting the total balance. We don't own to exploit the contract. So for contract A, the storage, we've got a balance of 200. So at this point, contract B can either drop the response from the withdrawal function or invoke a fallback function. A fallback function is a reserved function in Solidity that can appear once in a single contract. Function is executed when currency is sent with no other context or data. For example, what is happening in this example? The fallback function calls the withdrawal function again. While the original call to the function was never fully resolved, remember that the balance never was set back to 0, and the contract thinks the ether as its total balance when sending it, not divided into each account. So it will continue to send currency beyond the account's balance until the total balance is 0. Because the withdrawal function sends ether with no context or data, the fallback function will be called again, and thus an infinite loop will now occur. Now that we have covered how this vulnerability occurs and how to exploit it, let's put it to the test. We have provided you with a contract deployed Best Festival Company in a safe and controlled environment that allows you to deploy contracts as if they were on a public blockchain. Cool. All right, so this is a lot of new information, if I'm being completely honest. I have no experience with smart contracts or blockchains, so I'm so in the dark. It's a little scary. All right, let's go on to practical application. So we'll scroll up and we'll select download task files. So we're going to be using Remix IDE, which offers a safe and controlled environment to test and deploy contracts if they were on a public. So downloaded the attached folder and we've got Remix open. So we have two files, one gathered from Best Festival Company used to host their cryptocurrency. So that'll be Ether Store. And the other malicious contract that will attempt to exploit the re-entrancy vulnerability. So attack. Both contracts are legitimate Solidity contracts, but no need to worry if you need help understanding the program syntax behind each. They follow the same functionality and methodology we covered through this task, just translated to code. So getting familiar with the Remix environment. So when you first open Remix, you want to draw your attention to the left side. There will be a file explorer, search, Solidity compiler, and deployment navigation button respectively from top to bottom. We will spend most of our time in the deploy and run transaction menu, as it allows us to select from an environment, account, contract, and interact with contracts we have compiled. So importing the necessary contracts. To get started with the task, you'll need to import the task files provided to you. To do this, navigate to File Explorer, Default Workspace, load a local file into the current workspace. Okay, so left here, we've got File Explorer, we've got the default workplace, there's load a local file into the current workplace. So I've selected 1, Ether Store, and 2, the attack. So next, compiling the contracts. The next step is to compile the contracts. Navigate to the Solidity compiler and select this. From the drop-down compiler menu. So on the left-hand side, we've got Solidity compiler. So as long as it starts with 0.8.10 plus, so we've got that here. Okay, so we just need to make sure that in our file explorer that we've got our .sol files open, and then we can have either of them selected and then run compile. So it says we can ignore any of the warning signs, so that's fine. So we'll look at deploying and interacting with contracts. So now that we have contracts compiled, I'll just quickly do the attack too. Okay, now that we have the contracts compiled, they are ready to be deployed from the deployments tab. To the right is a screenshot of the deployments tab and labels that we will use to reference menu elements as we move throughout the deployment process. First, we must select a contract for deployment from the contract dropdown, label 6. So we'll go to the deployment and run transactions. So we'll start with the Ether Store. Under the contract dropdown, use the Ether Store. For deployment, you only need to press the deploy button. Okay. Cool. We can now interact with the contract underneath the deployed contracts subsection. To test the contract, we can deposit Ether into the contract to be added to the total balance. To deposit, insert a value in the value text box label 4, which is here. Select the currency denomination and the drop-down under label 5. Once setup is complete, you can deposit by pressing the deposit button label 10. Oh, okay. So here's our smart contract down here. Once we've put that in, now we can go deposit. Okay, all right. Note, when pressing the deposit button, this is a public function we are calling, just as if there were other contracts calling the function externally. So we've now successfully deployed our first contract and used it. You should see the balance update, label 9. Label 9 there. Okay. Now that we've deployed our first contract, switch to a different account, drop down label 2 and select a new account. So we've got this up here. So we were on this guy. I guess we'll just go over to the second one and repeat the same steps. So we don't need to deploy, right? We can just go like 15. Okay, no, we hit deploy. So now we have our 2 contracts. And then if I go 15 and then go deposit, there we've got our 2 contracts with different balances. Okay. This time you'll be exploiting the original contract and should see the exploit actively occur. We have provided a summary of the steps to deploy and interact with the contract below. Step 1, select the contract you want to deploy from the contract drop-down menu under label 6. I'm just going to keep on Ether Store, right? Deploy the contract by pressing the deploy button. So we'll do another one. So this is the one that we're going to exploit. You need to provide a reference to the contract you are targeting before deploying the attack. To accomplish this, copy the address of Ether Store from label 11. So that's this. So that's the address for our contract. And paste the value in the text box under label 8. Oh, okay. I should be on attack. We go attack and we can paste that in here. So our contracts are still there. Okay. Step 3, confirm the contract was deployed and the attack function can be seen from the deployed contracts subsection. Okay, so I've hit deploy and we can see that there's this one here. So it should be attacking this one. Step 4, execute and or interact with the contracts function. Note that most functions require some form of value input to execute a function properly. So, and we put 10 and okay, there's our flag. So that does us for the day. I'll be honest, I have no idea what happened. I think I need to go over this like 20 more times to fully understand. This is so confusing to me. If you're still watching this, I genuinely appreciate it. But yeah, hey, thanks for checking out this video. I hope you're understanding this a bit better than I am. This is just new stuff, and I guess, hey, that's just what it's like when we're learning something new. So I'm not going to stress about it, but thank you for watching. It would mean a lot if you leave a like and subscribe, and if you ding that bell for some reason. And I'm going to let YouTube suggest a video for you, so that's up on the screen along with a playlist that I think you'll enjoy. Otherwise, thanks for checking out the video, and I will see you in the next one. Okay, see you later.